Welcome, class. Good morning. It is Tuesday, May 26th. Coronachem day 36 for period 1. I asked you to do some conversions for homework yesterday, and I'll give you those answers right now. So the first one is to convert 25.5 milligrams into grams. The conversion factor from grams to milligrams, from milligrams to grams rather, is 1 gram per 1,000 milligrams. You'll notice I put milligrams in the denominator so that I can cancel milligrams. This is equal to 10 to the minus 3. I mean this whole thing. This is 10 to the 3, but when I put 10 to the 3 upstairs in this equation, what we get is this, 25.5 times 10 to the negative 3. And then the only thing that doesn't cancel is grams. And then I'm going to rewrite that in scientific notation. So I'm going to replace the decimal place so that you get 2.55. I've made this 10 times smaller, so I got to make this 10 times bigger. And you get that as a final answer. B. We're asked to convert meters into nanometers, and they give you 4.0 times 10 to the negative 10 meters. The conversion factor to go to nanometers from meters is 10 to the 9 nanometers per 1 meter. So that equals 10 to the minus 10 times 10 to the positive 9 gives you 10 to the minus 1 as an answer. So you're going to get 4.0 times 10 to the minus 1. Meters cancel, so the answer is in nanometers, or you could say, because 10 to the minus 1 is equal to 1/10. 1/10 of 4 is 4 over 10, or 0.4 nanometers. Make sure there should be 2 sig figs there. 0.40 nanometers. I didn't have enough room to write it. Part C. You're starting off with 0.575 millimeters times, and you want to convert it to micrometers. First we'll go to meters, because I don't know the conversion factor from, well actually I do, but I want to show you what to do when you're stuck. See, I know that there's 1,000 micrometers per 1 millimeter. But probably most people don't know that. But you can easily figure out that there are 1,000 millimeters in a meter, because milli means 1,000. And from there you can also go to micrometers, which is 1,000,000 per meter. So you do it in 2 steps rather than 1 step if you're not familiar with the conversions between the different steps. So I'll show you how I would do it, because I know it. I would say times 1,000 micrometers per 1 millimeter, and that right away gives you the correct answer. You're going to have 0.575 times 10 to the 3, because remember 1,000 is 10 to the 3 micrometers, and then you would convert it to 5.75. You made this 10 times bigger, so you got to make this 10 times smaller, and you get 5.75 times 10 to the 2 micrometers. But I'll show you how to do it in 2 steps if you don't know the conversion factor between micrometers and millimeters. And what you would do is first go to meters. So you have 0.575 millimeters times 1 meter per 1,000 millimeters, and that would get you to meters, but don't get the final answer yet. And then if you want to go to micrometers, you're going to say 10 to the 6 micrometers per 1 meter. It allows you to cancel meters as well, and the final answer will be 10 to the negative 3 times 10 to the positive 6 is going to give you 10 to the positive 3, so it'll give you 0.575 times 10 to the positive 3 micrometers, which then of course works out to 5.75 times 10 to the power of 2 micrometers as your final answer. Same strategy to go from here to there as it did from here to there. The next one I was going to do with you was 126, which is just more practice along these lines. I find that you can never get enough of this with your students because they never seem very confident with it. The problem that students fall into is they follow the teacher on the board and it seems pretty rational and easy to understand, but when it comes to doing it themselves, they seem to fall flat on their face. So the key here is to do the practice so that you know that you can actually do it. 126A. You start off with 9.5 times 10 to the minus 2 kilograms times, you're asked to go to grams, so there's 1,000 grams per kilogram. Kilograms cancel, and this is 10 to the 3. So 10 to the 3 times 10 to the negative 2 is 10 to the positive 1. So you get 9.5 times 10 to the positive 1 grams as your answer, and we all know that's 95 because 10 to the 1 is 10. 9.5 times 10 gives you 95. B. You're asked to convert from micrometers to nanometers. Again, this is a question you can do in 2 steps if you're not familiar. So you're going to first say there's 1 meter per 10 to the 6 micrometers, and then you're going to say 10 to the 9 nanometers per 1 meter, so that allows you to cancel micrometers, meters, and meters, and you get an answer in nanometers. This 10 to the 6 becomes 10 to the negative 6 when you bring it upstairs. So 10 to the negative 6 and 10 to the positive 9 gives you 10 to the positive 3. So you're going to have an answer 0.0023 times 10 to the positive 3, which is basically 1,000. So you're multiplying this by 1,000. So move that decimal 3 times. 1, 2, 3. Your answer is 2.3. You don't have to write times 10 anything. Nanometers. I believe it's 2 sig figs. Yeah. Last one. 7.25 times 10 to the negative 4 seconds. You're asked to convert it to milliseconds. There are 1,000 milliseconds per 1 second. Seconds cancel. This is 10 to the 3. So 10 to the negative 4 times 10 to the positive 3 gives you 10 to the negative 1. So 7.25 times 10 to the negative 1. This becomes, it's like 1/10, so this becomes 0.725 milliseconds. Now, I'm going to move you into some density calculations for number 127. I'll just do the first one with you to get you primed, and then you can do the rest of that problem for homework. And then I'm going to start reviewing chapter 2. I must warn you, it's not going to be an extensive review. I'm just giving a very rough sort of helicopter view, eagle's eye view of chapter 2, just to show you how all the ideas connect. And then you should read through the chapter again in preparation for the final exam and give you a basic understanding of what happened in early days of chemistry. So 127A is asking, a sample of carbon tetrachloride, a liquid once used in dry cleaning, has a mass of 39.73 grams and a volume of 25 milliliters at 25 degrees Celsius. What is its density at this temperature? Will carbon tetrachloride float on water? Materials that are less dense than water will float. So we're going to use the density equation. Density equals mass over volume. They say that the mass of the sample is 39.73 grams, and that it's a 25 milliliter sample. So that gives you a density of 1.5892 grams per milliliter, and we know the density of water is very close to 1. When you go to significant figures, it comes to 1.59 grams per milliliter. So carbon tetrachloride is denser than water, and so it sinks. Carbon tetrachloride will not float. So do B and C are the same question for homework. Now let's look at chapter 2. Chapter 2 talks about atoms and molecules. Now at the beginning of chemistry. Sort of the state of the art was what Dalton's theory had said. Dalton had put together all the key ideas that were known in chemistry, and he penned his atomic theory of matter. 4 ideas were that each element is composed of extremely small particles called atoms, so that he believed in atomism. Before that time, there was question about whether matter was continuous or whether it was composed of very tiny things that looked continuous. Just like when you look at your TV screen, is that TV's image continuous, or if you get close enough do you see individual dots? They had the same question when it came to matter. Turns out matter is made of atoms, so if you get close enough you see the little dots. 2, all atoms of a given element are identical to one another in mass and other properties, but the atoms of one element are different from the atoms of all other elements. So each element has its distinct identity and properties, chemical and physical. 3, atoms of an element are not changed into atoms of a different element by chemical reactions. This is a key idea. Water doesn't turn into carbon dioxide. Okay? Water is made of hydrogen and oxygen. To get carbon dioxide, you need some carbon. If there's no carbon, you're not going to get carbon dioxide. So the elements retain their identity. It's like pieces of Lego. If you could build a house using Legos, but then you could break up the house and then build an airplane with the same Legos. The Legos haven't changed. You've just arranged them in a different pattern. 3, atoms of an element are not changed. Okay, we just did that. Atoms are neither created nor destroyed in chemical reactions. So chemical reactions had no effect on the identity of atoms. That's the province of nuclear chemistry. That's when you have radioactivity and you have thermonuclear fission or fusion. Then the temperatures are high enough and the conditions extreme enough so that you actually alter the nuclei. But if the nuclei remain unchanged, the atom is the same. 4, compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kind of atoms. So water is always H2O. It's not, if it's not H2O, it's not water. So that was the state of the art in the early 1800s. Then what happened? They discovered the cathode ray tube. What's a cathode ray tube? A cathode ray tube is basically a glass tube that's been evacuated, meaning all the air has been sucked out of it. So until the middle of the 18th century or so, or early 18th century, they didn't have vacuum pumps that were good enough to suck all the air out of a container. Once they developed that capacity though, they started doing experiments with this vacuum. And they discovered that if you put a high voltage transformer on either end of this evacuated tube, you got a green line that would traverse the whole tube. And that green line was mysterious. They didn't know what it was composed of, but they said there had to be something coming out of the atoms to do that. Turns out it was electrons, but they didn't know what it was initially. They also realized that it reacted to magnetic and electric fields. You could bend the ray. The cathode ray tube is what constitutes the early technology for televisions. It was basically an electron gun, and the electrons are aimed at the other side of the tube, which is what we see as the screen. And when the electrons hit the back side of the screen, they have chemical substances that give off a flash of light. And depending on the chemical substance, you can get a red light or blue light or a green light. That's how they made RGB color monitors. And the electron gun was made to shoot lines and redraw the television screen 60 times a second. So it emitted very high frequency. I remember in the early TVs when I was in my teens and 20s, I could hear the TVs from outside on the driveway. I literally could hear that high-pitched noise that old TVs made. Now, as I've gotten older, I've lost those higher frequencies. But I know that sometimes when I turn on the TV in the classroom, I have the old TV that I used when I was in my teens and 20s, some of the kids complain and say, "Sir, what's that noise?" It's the TV, it's the old technology. The cathode ray tubes emitted a very high-pitched frequency that only teenagers and children could hear. Anyway, they discovered with the cathode ray tube that there had to be some particle-y atom that was reacting to these properties. It was a negatively charged particle. It was very light. You could bend it with magnets and with electric fields. And eventually, Thomson discovered the ratio between the charge on the particles and their mass. He didn't know the charge and he didn't know the mass, but he knew the ratio between the charge and the mass because he was able to bend the beam, and based on how much the beam bent, he was able to do that calculation. Later on, a guy by the name of Millikan did a very clever experiment. We had tiny little drops of oil dropping in a vacuum chamber, and some of the drops were so tiny they could actually pick up one electron, and by playing with a magnetic charge on two plates where those electrically charged droplets were moving, he could get the drops to stop. And by doing that, he was able to calculate the charge of one electron. Actually, I'm not sure if there was a vacuum inside the plates. Maybe it wasn't a vacuum. It may have been just that the drops are falling, because if there was a total vacuum, drops wouldn't fall slow, but they would drop. They would drop quickly. So it probably was not a vacuum. It was simply two plates that were charged, and the tiny droplets would fall slowly, and he was able to stop them from falling by playing with the charge. So he was able to calculate the actual charge on one electron. Now they had the charge to mass ratio that Thomson had found, the charge that Millikan had found, and they were able to calculate the mass of the electron, and then things started to pick up pace after that. They shortly after that, they discovered radioactivity. They discovered that some atoms, emit particles. And usually there are two types of particles that they were acquainted with. Actually, there's also a third, there's neutrons, and actually it's even more complicated than that, but I'm not going to get into it. There were alpha particles and beta particles that they called radiation. So alpha particles are basically a helium nucleus without electrons, right? So it's a helium nucleus fired out of the nucleus at high speed at 20,000 kilometers per second, around there. So it has an enormous amount of energy, and they don't fly very far, but they can do quite a lot of damage whatever they hit. And the other type of particle they discovered was called beta radiation. It was basically an electron with lots of kinetic energy. So that was how the nucleus was emitting the enormous amounts of energy involved in the breaking up of the forces that hold the nucleus together. Because think about this, the nucleus is composed of protons and neutrons. We know that now. Back then they were guessing about what was going on in the nucleus, so many people came pretty close in theorizing what was going on. But think about it, there's a bunch of positively charged particles all stuck together in the nucleus. So we all know that positively charged particles repel each other. So what's holding them together, so close together in the nucleus? Well, there's another force we didn't know about called the strong nuclear force, and that nuclear force is strong enough to overcome the electrostatic repulsions, but it only works over very, very short distances. So if the nucleus gets jostled enough so that it distorts its shape, then the electrostatic force can overcome the strong nuclear force, and the nucleus flies apart, and that's how you get radioactivity and fission and all the other things we call nuclear chemistry. So once they discovered these particles, a clever scientist by the name of Ernest Rutherford, decided to do experiments using known emitters of alpha particles. So what he did is he took a big lead block, drilled a hole in it to make a little skinny tube, and he placed a radioactive piece of, I think it was polonium, at the very back of that long skinny hole that he had drilled in the lead block. His idea was he would get that lead block to mask all the radiation coming out of the particle in every direction, and he would force it only to shoot forward. And then he aimed the opening of that lead block at a piece of gold foil, a very thin piece of gold foil. And he theorized that because gold has heavy nuclei, it should be able to stop all these alpha particles shooting out of the block. Instead, what happened is 99% or more of the particles shot right through. But, and this is the more interesting part, a tiny percentage of the particles that hit the foil bounced right back. So his characterization of the experiment was like firing a howitzer at a piece of tissue paper. Howitzers were these giant cannons that were used during the war. They had bullets about this big, and whatever they would hit, they would devastate. So he said it was the equivalent of firing a howitzer at a piece of tissue paper and having it bounce back. That was a very good analogy of what was going on. what it pointed out was that all the mass of the nuclei of the gold atoms was concentrated in a tiny area called the nucleus. And most of the atom is empty space. So most of the particles was flying through because they were missing the nuclei. Because the nucleus of the atom is only about 1/10,000th of the cross section of the whole atom. So let's give you an analogy. If a football field is 100 meters in length, it's actually 100 yards, but anyway, let's count the end zone so we get 100 meters. 1/10,000th of 100 meters is 1/100th of a meter. So it's like 1 centimeter. So take a BB, which is not even 1 centimeter. A BB is half a centimeter. Okay, so 2 BBs side by side equal, so like a P in a football field is the nucleus compared to the whole atom. But all the mass of the whole nucleus of the whole atom is concentrated into that tiny pea-sized, compared to a football field, entity called the nucleus. So that means if you were to take matter, and this is what happens in a neutron star basically, all the matter that composes the star is compressed into the size of the nucleus. So now the nuclei are actually touching each other. That's what happens in a neutron star. That never happens in normal matter. None of the matter that we see and interact with has nuclei touching. What are touching are the fields of the electrons flying around the nucleus. Okay? So those fields interfere and they don't allow the nucleus to come within proximity of each other. But if you apply enough pressure, you can force those electrons into the nucleus, and now what you have is nucleus to nucleus touching, and it makes the matter 10,000 to the power of 3 times more dense. So the density of a neutron star is due to the fact that you have neutrons touching each other. You don't have normal matter anymore. You have neutronium. It sounds like something out of science fiction. And what happens is 10,000 to the power of 3 is 10 to the power of 4 to the power of 3. So the matter is 10 to the 12 times denser than normal. And that's why, whenever you read about astronomy, you hear about stars that have, a teaspoon of neutron star would weigh X millions of tons. Let's do an analogy. If something is 10 to the 12, that's 1 trillion times denser. So something that would weigh 1 centimeter, say a 1 centimeter cube of water would weigh 1 gram. Now you take the same size of neutronium and it would weigh 1 trillion grams, or 1 billion kilograms, or 1 million tons. 1 million tons. So something the size of a pea would weigh 1 million tons. So you can understand that it's not what we call a regular state of matter. Anyway, that's enough about the nuclear atom and radioactivity. The modern view of the atom that they came to understand through all these experiments was that the nucleus is composed of protons and neutrons, and then the electrons are what compose the rest of the atom. Rutherford had another way, a clever way of putting it. It's like a few flies inside of a cathedral. So the electrons are the flies, and the protons and the neutrons are that pea-sized thing at the middle of a football field by relative size. Typically, an atom has 4 areas. The atom symbol. Okay, the atom symbol has always got a capital letter for the first part and lowercase for the second part, unless it's a single letter name, like for example potassium, then it's just 1 capital letter. You never have 3 letters in a name, and I know it says at the bottom of the table things like 104 unilquadium. That's not a name, that's a number in Latin. Unilquadium means 140ium, because they didn't have a name for it, so they just gave it they just said a number in Latin and put ium at the end of it. Unilquadium, unilpentium, 104ium, 105ium, until we find a proper name. Now they're all named up to 118. Anyway, if you look at lithium, this area is reserved for the number of protons in the atom. Always. Bottom left. Top left is for protons plus neutrons. It's called the mass number. Okay, this is called the atomic number. Here's for the charge, if there is one, and this is for how many of the atom. So if you have two of them, you put a 2 and so on. And that is your diagram of the atom. I'm going to stop there for today. You know what your homework is, and we'll meet up again tomorrow. I'll continue from page 43 or so of chapter 2. I would urge you to start rereading your chapters, but don't read through them like a bulldozer. Use the technique I taught you for reading through the chapters. See you tomorrow.